Now, just like in chemistry, there's the conservation of matter, we have the conservation of charge, meaning charge is never created or destroyed. It's just simply shifting from one object to another. If you rub amber, which is an old-fashioned stone, with a cloth, all right, you look at their charges like +2, -2, that's neutral, and +3, -3, overall that's neutral. But you rub them together, you can end up having a transfer of charge. So overall the amber might have an overall -2 charge, but that means then that the cloth has to have an overall +2 charge. So again, to recap, your charge is just simply shifting, but we never create or destroy, it just moves. So how does an atom that's electric and neutral actually become charged? The simple idea is that you either have more positives or more negatives to give it a positive or negative charge, which means you either have to remove or add protons or electrons. Well, if you know protons and neutrons are pretty stuck in the nucleus, that's because of something you've learned about called the strong nuclear force. Well, that means that the electrons, which are on the outside, are much easier to remove. So if we're gaining or losing electrons, that tends to be what's going to determine whether we have a positive or negative charge. There are a few ways to actually charge an object. One is by the term induction, and that means that you're actually shifting the charges just by having another charged particle nearby. If you take a look at this example, these are two metal spheres near each other. They both have positive and negative charges floating around, but they're technically neutral, so you can't see their separate positive and negative charges. Now, when you bring a negatively charged balloon near them, what happens? Well, it repels the electrons, the negative charged electrons, and pushes it to the right side, which does what? Leaves behind more positive charges. So by induction, by bringing this negative charge towards the sphere, you now have a more positively charged sphere and a more negatively charged sphere on sphere B. That means if you separate them, as you do in this part, since there were more negatives over here and left behind more positive charge, you end up getting a positively charged sphere versus a negatively charged sphere. How? All by induction, not by actually touching this balloon to the spheres, but bringing it near it, you repel the electrons and push the negative charge towards the right. That's what we call induction. Now, conduction is opposite or different. Instead of being near, conduction means you're actually touching. So take, for example, this sphere. It's still a zero charge, and you bring near it now and touch a positively charged pi tin, something we will do in our actual lab. By bringing the positively charged pi tin towards the sphere, any extra loose negative charges from this neutral sphere will want to naturally work its way over to the pi tin. By doing that, you had some of the electrons leave and leave behind a positive charge, which means that overall your sphere now has a positive charge. Remember, if you have an electron that leaves, you now leave behind extra protons. By having extra protons that aren't canceled out with the negative electrons, you give an overall positive charge. If for some reason you add electrons, that means you have extra electrons, which means you have an extra negative charge or an overall negative charge. Think about that. That's just chemistry review right there. Grounding is an interesting phenomenon. Electrons naturally want to spread out. So if you have a positively charged sphere that's touching the ground, electrons from the ground will naturally flow to neutralize or cancel out the positive charge in this sphere. And vice versa. If you have an overall negatively charged sphere that's touching the ground, since the ground is so large and electrons are spread out, electrons will flow to the ground to alleviate some of that charge. So grounding is an important concept when we want to get rid of our charge. We're going to be doing a lab that kind of investigates conduction and induction. And to do that, we're going to be using something called a pith ball, which almost looks like a little tiny styrofoam ball. At first, that pith ball is going to be neutral, which means that it does have positive and negative charges, but they cancel each other out, so it's neutral. Now, say you bring a negative rod near it, but not touch it. This is what would be called induction. Induction means that you're bringing a charge near it without touching, but you're affecting the other object. In this case, electrons, again, are going to repel to the left side of the pith ball, which means that you're going to have more of a positive side on the right side, which will naturally have the negative rod and the positive end of the ball attract each other. Now, if they are attracting each other from over here, like we said, and they eventually make contact with each other, what happens? Well, the negatively charged rod starts pushing some of its electrons onto the pith ball. By doing that, you now make this ball overall a negative charge. And since it's near a negatively charged rod, we know that like charges repel, and you end up getting now the pith ball to repel from the rod. So it's a strange phenomenon. In a few quick seconds, you go from attracting through induction to repelling because of conduction. Think about that, and of course, it'll take some time, but we'll learn that even more in our lab. Another thing you're going to do in your static electricity lab is actually make a pie tin turn to a positive charge. To do that, you're actually going to take just a simple, cheap foam plate and you're going to rub it with fur. Fur is going to actually, believe it or not, donate electrons to the foam plate. You will then take an insulated pie tin that is metal and you will bring it close to the negatively charged foam plate. By doing that through induction, you are actually going to make the bottom of the pie tin more positive because it's near the negatively charged foam plate. And you're going to push the top end of the pie tin to be more negative. And that's through, this one is induction. Then when you touch it with your finger, you are going to ground it or pull out extra negative charge. And when you do so, you end up making the pie tin overall a positive charge. Now when you bring it towards the negatively charged foam plate, it should attract to it and stick. Think of that process again. We donate electrons in step 1. Step 2, through induction, you push the negative charges towards the top of the pie tin and give it a partial positive charge on the bottom. In step 3, through grounding and touching it, you suck out, in a way, some of the extra negative charged electrons. And what do you do in step 4 and 5? You leave behind more positive charge, which makes the plate a positive charged object. Another part of the lab will be using of an electroscope. If the leaves end up having the same charge in the bottom, their metal leaves, as we call them, push apart. Think of them as like tiny pieces of foil. Now, if someone is pulling on that charge upwards, the leaves are going to actually push together more. We'll do a lot of experiments with this to see just how the transfer of charge actually affects the electroscope. This concludes our electrostatics beginning, and we kind of did a pre-lab as well into something we'll be doing in class. Thanks for listening. Think about conduction, induction, grounding, and opposites attract and like charges repel, and at least from there we'll be at a good start. Don't forget charges, which is noted by the letter Q, is also measured in the unit of coulombs. Have a great day, and thanks for listening.